Okay, so this is part 2 of the number systems video lesson, and we're going to be going the other way around. So now we're going to do decimal to binary. And I will switch back to the PowerPoint or the presentation after 2 examples here. So decimal to binary, we're going the other way around, and we'll still be using that chart, that powers of 2 table. So here's an example. So example number 1 for decimal to binary, convert 353 base 10 to binary. So to do this, what we're going to do is take a look at that powers of 2 chart that we had up on the last slide, and I'm going to recreate it over here. And I only really need one column, and that's the expanded column. So I'll just put powers of 2. So we start with 2 to the power of 0, which is 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4, and we just keep going. And here's the secret: we're just doubling the number. That's a 2. As you go up by powers of 2, your math teacher will tell you that you just double the number to get the next value in the table. 4, 8, 8 plus 8, 8 doubled 8 is 16. Double it again, 32, 64. And we only have to go as far as, we should go past 353. So 256. And then double it again, 512. You can use a calculator to come up with this table if you want. Just make sure that you're doubling the number each time. I don't need to go any further, and you'll see why in a minute, because you only have to go as large as what the number is. If I was to go further, 1024, 1024, 2048, etc. We won't have to go any higher than that most of the time. So 350, what we're going to do is we want to chip away at this number that's a decimal number. We want to deconstruct it using these powers of 2, because we know these powers of 2 are represented by 1s in the binary number system depending on their placeholder. So if we have 356, we want to find the largest number on this table that we can subtract from, that we can use to subtract without going negative. So 512 is too big, so we're going to use 256. So we've used 256, which is a power of 2, to knock this number down. And as soon as we get it down to 0, we'll know that we're finished. Okay, so 353, take away 256, 97. So we get 97, and feel free to use a calculator. 97, take away the largest number on the table without going negative, 64. So we have 33. So far we've used 256 and 64 from the table. 32 is the largest number that we can use now. We have left with 1. And don't forget to go all the way to 0. All these go all the way to 0. So now we've knocked the number down to 0, and now we're going to circle all the values that we used that were powers of 2. All right, so those are the placeholders in the binary number that are in our binary number that are set to 1. Everything else is set to 0. So I'm just going to do this box, and you'll see in a minute. It just helps to understand. There, I'll have to get used to checking that you can actually see what I'm doing. So I'm going to go freehand here, but we have the first power of 2 that we could have used, that is in the placeholder for our binary number. So these are going to be this is going to be the binary number. These are going to be the placeholders. This is the 1's placeholder, this is the 2's placeholder, the 4's, the 8's. These are just the powers of 2, 16, 32, 64. Notice I did it right to left. Just like in a decimal number you learn from elementary school or whenever in grade 3 or 4, whenever it was, the 1's place, the 10's place, the 100's place, that would be decimal numbers. Well, these are the placeholders for binary numbers. They're always the same. They're always like this. 256. I'm going to stop there. So if we use the placeholder in our subtraction when we're knocking the number down, we're going to put a 1. So we did use 256. We used 64, we used 32, and we also used 1. We didn't use any of the other ones, so put a 0 in those locations. And that's our binary number. So therefore, 353 base 10 is equal to 1011000001 base 2. That's your final solution. Okay, so that's our first example. I'll do one more example of decimal to binary for this video, and then we'll complete the number systems lesson. Okay, example 2, decimal to binary still. Convert. Let's do this. 511 base 10 to binary. So this is going to be a bit of a doozy because I want you to notice 511 is just one shy of 512. And 512 is a power of 2. If it was 512, let's just do this inside here. So let's say that we had to convert 512 to binary. Well, we would take the largest number on the table. 512 is a number on the table. So we do take away 512 and boom, we're done. So that would mean that we only use one number to get to 0. So that means that, and I'm looking at my table here, I would have 1 in the 512's place, 0 in the 256 place, 0 in the 128. It would be all zeros, 64, 32, 16, 8, 4, 2, 0. So that would be base 2. That would be what the number would be in binary if it was 512. But as you can see, 511 is just one less than that. If you can see a quick way to do this without what I'm about to do, feel free to use that. I'll explain it later. But here's the most straightforward way. I'm sure there's probably 1 or 2 of you in the class that can see that there's a shortcut now to find what 511 is. But I'm going to do it the long way just because we want to get used to this process. That's the whole point of this lesson. 512 take away, and from the table, so you can see the table that we did, the powers of 2 table, 256 is the largest number, right? So 256. And so we're left with 255. 255, hey guys, sometimes when you're videotaping you get distracted or there's interruptions, but I'll try to continue from where I left off. So 255, the next one on the table, it can't be 256, has to be 128. And that is going to be, in the calculator, 127. 255 take away 128. And now we have to subtract the largest value in the table again. Well, it looks like it's going to be 64. So you can see that we're just one shy each time, and it's kind of annoying, but that's the way it goes. 64. So we're left with 32. No, we're not left with 32. I'm sorry. We're left with 63. 63. 63 take away, and 32 is the largest number on the table. So now we're going to be left with 31 take away, and 16 is the next largest number on the table. So take away 16, we're left with 15. 15 take away, the largest number on the powers of 2 table is now 8. We're left with 7. 7 take away. The largest number on the powers of 2 table is 4. So we're left with 3. Take away the largest number, 2. We're left with 1. Finally, 1 take away 1 is 0. Whatever you do, make sure that you never use the same. So I'm going to circle all the numbers. These numbers I'm circling, the ones that you used from the table, make sure you never use the same number twice, or you know you did something wrong, right? If that makes sense. Okay, so all these numbers are placeholders in our value, in our solution. So I'm going to make that little thing again. The largest number or placeholder we have to deal with is, as you can see, 256. So I'm going to put 256 here on the left side. It might be easier for you if you're going to be doing it this way. Start with 1 on the right side and work your way down. Just make sure that the smallest placeholder is on the right. A common mistake is to have the 1 on the left side, but the least significant digit, the ones place, has to be on the right-hand side, just like with a decimal number. Okay, so I'm going to do it from left to right. If that's too confusing, again, do it right to left. So here's our placeholders. We're using 256, we're using 128, we're using 64, we're using 32. In fact, we're using all of these placeholders, right?
Extension 1002, Rui, please call 1002.
We're using all of these placeholders. So that's our number. Therefore, 512 base 10 is equal to, hopefully you can see that. See, I did, you couldn't see all those at the bottom for a second, but they are all there. Guys, I just realized that this should say TEJ, shouldn't it? So I'm going to fix that right now. So it says TEJ. That's a little bit confusing. You're going to find that your teachers are all a little bit confused right now. We're TEJ 3M or TEJ 4M because this is a review for TEJ 4M. So I'm just going to put TEJ. And if you're in TEJ 3M, this is the first time you're seeing this. Okay, so we're just about done. This is and then we're going to switch over. So this is equal to 111, 111, 111, base 2. Going back up to here, some of you might have been able to say, well, if that's what the number is in base 2, if it's 512, 511 is just one less than that, right? So we've got, how many zeros do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. So we have a 10-digit number here, binary. Here we have a 9-digit number and it's all ones. This number is one less than that. Just something to think about, not really, you don't need to think about that too hard, but let's complete the lesson now. So now I'm going to switch over to our number systems presentation. We already did converting decimal to binary. We already did the other way. This is the one of the last slides in this presentation now, bits and bytes. So I want you to know that a kilobyte is actually 1,024 bytes. Now, you know, when you're driving and you see a kilometer, it's 1,000. A kilometer is 1,000 meters. So logically, you'd think that a kilobyte should be 1,000 bytes. That's not the case. It's actually 1,024, and that's because everything inside of the computer is in binary. So they could have made it 1,000, but then they would have been wasting 24 bytes. So back when computers were invented, and even now, it was so important, it was more important back then to be as efficient as possible and not waste anything. Everything was so expensive back then. A computer that could barely even be a calculator was thousands of dollars back in the 1950s and 40s, whenever this technology came out. The architecture of the basic computer and the way that bits and bytes are used in mathematics, the foundations are still the same as they were way back 70, 80 years ago when this first came out. Everything is still binary. That might change in the future. Maybe it'll be trinary. Maybe it'll be, they're talking about quantum computing. It's totally not part of the lesson, but it kind of makes you think. Maybe you could have a 0 and a 1, and then you could have a state in between. Megabyte, you have to know megabytes, 1,024 kilobytes. And that's because 2 to the power of 10 is 1,024. 1,000 doesn't fit in evenly to the binary numbering system, but 1,024 does. The one before that, if they would have had it one less digit, would have been 512, and you can see that on the table. Okay, so and let's see here, we've got so some equivalencies. You can pause this and look at it, and I'm going to recommend you do. I could read it out. Kilobyte, kilo means 1,000, megabyte, mega means million, gigabyte, giga means million, and terabyte, tera means trillion. So I think that this is going to be what I'm going to ask you to do next. And let's see here. We're going to do 1 through 8, and I will make this available as a document for you to do on paper. This unit, a lot on paper.